Hi everyone. In a previous video, I was able to share with you the comparison of OpenCL versus ISPC on one of these platforms with the this time exposure application that I've been using to do some benchmarking and kind of have a application that may have some real life usage, but use it for comparing platforms and be able to do the benchmarking and performance analysis in this context. In any case, what you're seeing here is it's a cross-platform application because of the APIs that I use. They're available on Windows, Mac, and Linux. And so here you see that I'm running it on Windows, and I'm using it just to capture my image. I can also run it, but the purpose of this video is to focus on the Jetson Nano. So I'm just going to focus on the Jetson Nano, but I wanted to point out that the application is also I can run it on different platforms. Maybe down the line I can do a comparison with Windows, but for now the subject is Jetson Nano, so I'm going to switch to the Jetson Nano platform. So here you see the Jetson Nano desktop, and I'm going to run the application, and what you can see is I've added a couple of options here. Unfortunately, maybe it's not very visible, but there's some runtime options that I added that lets me switch between ISPC, OpenCL, and Cuda, and also C++. So these are the 4 different compute methods and options that I have implemented. And on the right, as you can see, is the on the right picture here, as you can see, is the live color picture. There on the left is the 10-minute time exposure. I have a DFT of the grayscale version of the color and a DFT of the time exposure image. If we switch here, I've also added some information about the devices. For example, for OpenCL, as you can see, I use the CPU cores. So the OpenCL kernel is running on all the CPU cores, and it's using the pthread library. There are 307,200 pixels in each picture. So this picture is 640 by 480. That amounts to 307,200 pixels. And for the OpenCL kernel, that's the global work size, and the local work size is 4096. So that's those are the OpenCL kernel launch configurations. And then for Cuda, I've added some information that I show. So on the Cuda, the device is device 0. It's a Tegra X1. It's a compute capability 5.3, so it's a Maxwell architecture. There is only one multiprocessor on the GPU, and based on this compute capability 5.3, I know that it's 128 cores for each multiprocessor. Since there's only one multiprocessor, there's a total of 128 cores on the GPU. Warp size is 32, as it is for all the Cuda devices so far. And that means that if you divide 128 by 32, there are 4 warps on this per multiprocessor. But since there's only one multiprocessor, that means the entire GPU has 4 warps. The GPU attributes that I get back give me some of this other information like warp size and max thread blocks. max threads per block is 1024, and a max threads per multiprocessor is 2048. Based on this information, I choose this grid dimensions. So there are 128 thread blocks, and each thread block has 1,024 threads. If you multiply 128 by 1024, you get a grid stride or grid size of 131,072, and I have implemented a Cuda kernel with a grid stride, so each kernel can compute more than 1 pixel's worth of data, and do this in parallel. In this grid, as a result, if you divide this number by 32, or this grid will have 4,096 warps in it. Based on this kernel configuration, I have an occupancy ratio of 1. I use the Cuda occupancy APIs to find out that the maximum active blocks that I can have for my kernel is 2. So if I multiply 2 blocks by 1024, I get 2048 active threads. And if I divide that by 32, I get a maximum of 64 active warps. So some of this information I may or may not use right now. I've chosen these numbers for the grid dimension and the block dimension. This is the number of blocks in the grid, and this is the number of threads in each block. So I get a good occupancy ratio, and but I may be able to use some of this information later, so I decided to print it out and also know what device I'm running on. So previously, in the previous videos, I didn't show this information. So anyways, going forward with this, it's been running, and as you can see here, I've checked the checkbox for CUDA computation. So in this video, I'm going to take a look at this column, which is the only thing that these checkboxes are going to affect, is going to be the values of these columns. These other DFT calculations are all done on the CPU using using ISPC. So that's not going to change when I change these variables, change these parameters. But now that I have these options to be able to change at runtime, I can do a better comparison. It's a little bit easier, and I'm using the same data. I don't have to start and stop the program. So that's an improvement since the previous videos. I've also added a reset button, so I can reset the time exposure to start calculating from fresh. But based on so far, in the time that I've been running it, it has captured 3,890 frames. Until 6,000 frames are captured, that's 10 minutes worth of frames. Every frame that's processed requires a buffer allocation, and that's done at every loop. After that, these buffers are reused, so the overhead of that allocation from the heap goes away. But I just want to point out that until this turns into 6,000, that overhead is going to be there. So I may pause and wait for that to go to 6,000 before switching to other methods. I'm going to let it go till about a little bit after 6,000 frames, so that I can exclude the allocation overhead that happens per frame. Okay, so I'm starting it I'm starting to record it before 6,000 frames have been captured, but now at 6,000, I expect to see these numbers to be a little bit lower because there will be no more allocation from the heap. So right now, before the 6,000 mark, before this, the lines above it, and this one is, they're in the high 300 millisecond range for the timex count. But as soon as that allocation goes away, the count's dropping under to the low 300 milliseconds. So that's good. This is a good place where I mean, occasionally, yeah, maybe there's something else going on the system, and it seems like there are other there are times, I guess, it uses more time. All right. So in any case, now that I know that allocation is out of the picture, I'll let it. It's a good time for me to switch. I would say numbers that are in the 300 to 400 millisecond range are what I'm expecting. So the next thing that I'm going to do is I'm going to compare Cuda with OpenCL, and this is OpenCL on the CPU. As you can see, I've added these options where I can switch back and forth, and whenever I switch that, especially when the case where I was using the Cuda computation, I have to move this some of the data that resides on the GPU that doesn't come up. I have to move it up to the CPU so that the computation could go on seamlessly. And but now I've switched from Cuda to OpenCL, and I'll give it a little bit of time, and we'll let it. We'll see what the numbers are. But it's already looking a little bit lower than Cuda, and which was surprising to me, is because I expected to be able to parallelize this and get better results on the GPU, but it seems like this application is not suitable really that much for the GPU, at least, or maybe my Cuda programming implementation is not really tuning for Cuda, but I have tried a few things, but right now OpenCL kernel is performing better than my Cuda implementation. If I switch to ISPC, I can now compare whether OpenCL is better on the Jetson Nano platform for this application, or is ISPC better. I have both implementations, all four implementations: C++, ISPC, OpenCL, and Cuda. But from what I remember seeing is OpenCL is actually better on the Jetson Nano platform. Even though ISPC vectorization is pretty good, OpenCL kernels seem to give me a little bit of a better performance. With ISPC, as you can see, the numbers are in the high 290 something range, maybe a little 309. But if I go to OpenCL, so here's when I switched. Actually, I'm going to ignore this line and not count it, but this is where when I switched. This line is sort of a mix, because even though OpenCL is running on the CPU, it has its own data buffers that are separate from the buffers that the C++ and ISPC implementations use. C++ and ISPC implementations share the same CPU buffers that are allocated from heap, whereas OpenCL kernel uses its own device memory, but since the device is CPU, It's the same DRAM that the others use, but I'm not using the host buffers in the OpenCL kernels. But despite the fact that there is some syncing of the buffers, that is still the data has this captured image has to move to the buffers for OpenCL. The OpenCL kernels has to be launched, and that involves launching threads on the 4 CPU cores, and then they compute, and then they produce the grayscale image and then the time exposure image. And I then do the calculations of these DFTs and display them using OpenGL on the CPU. So this time is just basically, you can see, is in the 200 milliseconds for the OpenCL versus the 300 numbers. Or wait, I mean, it was, I guess, yeah, it was about 300 and some high 290s, whereas I saw a little bit lower. I don't know. It's marginal, but there is a bit of a difference. I think there is a slight advantage to OpenCL on the Jetson Nano platform. And now back to comparing to Cuda. I'm going to switch to Cuda. And this was the line where I switched. We can ignore the next line because that again involves moving some of the data that was being computed by the OpenCL kernel into the buffers that are on the GPU supposedly, and that movement happens during the line when I click the checkbox, but after that, now it's this line. The lines after that are the ones that I'm looking at. And as you can see, the numbers are higher for the Cuda kernel. Now, the Cuda kernel the Cuda implementation is currently using device buffers. That means I allocate buffers during setup, not at runtime. So there's no overhead for allocation, but there's an overhead here for moving the data. I have to move this image down to the GPU buffer. In this case, the GPU buffers are actually on the Jetson Nano platform. They're not on the GPU itself. They're actually system DRAM, because that integrated GPU is sharing the DRAM with the CPU, with the host platform. It just gets a chunk of memory for that buffer from the same DRAM that's available, and that's it has access to it. But I have to move this picture, which is captured into this buffer that's allocated from C++ heap, into that buffer that is supposedly on the device side, and then launch the kernel, the Cuda kernel, and let it compute. So then when I move the data back for display, that is actually taking a lot longer than OpenCL. And it makes sense because in the case of OpenCL, these OpenCL kernels are not running on the GPU, they're running on the CPU cores, so they have access to the DRAM, and the movement of data can be pretty quick, a lot quicker for them, because it's a CPU host-to-host move as opposed to host-to-device move. And regardless of the fact that all of that DRAM is on the CPU side, on the platform side, they're not inside the GPU. But as you can see, the Cuda kernel is running in the 300 millisecond to high 300s. Now I have two more options. Instead of using device memory, I can use unified memory, and that's also called managed, because to allocate the unified memory, you have to call Cuda malloc managed, and that gives you a buffer that's unified. well, I thought this would be better for me, and so I added the checkbox. So I'm going to switch to it, but I don't see the gain. It seems like it's actually more expensive to use unified memory in this application, in this particular application. Maybe let's mark this as the line that when I switched, and as you can see, the time goes up, and it makes sense because unified memory, the way it I guess it's implemented, is it requires page faults to determine, okay, how to sync up the data between Cuda kernels and the CPU code. So that those page faults happening, they're costing time. And as you can see, when I switch to managed memory, unified memory, the price for me went up. And again, for me, I'm sure if I just use the Cuda event start and Cuda event stop, if I use a Cuda stop and start and stop event and calculate the time using that mechanism, I might get better results, but I'm not interested at that low level timing because there's a lot of other code that has to run. So what I'm doing is I'm comparing 4 different functions, one for each implementation, one for C++ implementation of the time exposure method, one for ISPC, one for OpenCL, one for Cuda. So I start a timer before calling whichever method I'm using, and then I calculate the time using CPU timers. And it's the same timing mechanism, but it gives me apples to apples timing comparison, because that's what I'm interested in. Maybe the timing using NVProf or using Cuda events might give me lower level, whatever the GPU time is, but I want to know what is all the code that has to get executed. What does that cost? And it seems like if I use unified memory, somehow I'm assuming that the page faults are costing. But I do have another option, and that is using pinned memory. And this will basically allocate a buffer. So I'm going to switch to that. So pinned memory, I switched on this line, or let's say this line. So above it, we're running in the 400 range, 400 millisecond range mostly. And here, pinned memory, it seems like it's even more expensive. And I didn't expect that. I expected that pinned memory would be less expensive, because it makes sense from the descriptions on the Cuda development kit documentation. Well, if I allocate non-pageable pinned memory, that memory is going to sit there and it's never going to be paged out to disk. And so it makes sense that if I copy the camera frame that's captured from that into pinned memory, then I don't have to have the runtime drivers copy this to a buffer and then copy it to some pinned memory. It just goes from my C++ buffers directly to the pinned memory, and that gets transferred down to the CPU. But somehow here, as you can see, when I switch to pinned memory, I'm paying an even higher price, which is I'm in the 500 millisecond range. So looks like for this particular application with my particular implementation, and this is mostly still a naive implementation in Cuda. It's not really tuned, but I've tried some of these parameters for tuning, and I've determined that for my particular use case, I'm better off sticking with device memory and not using unified memory or pinned memory. As you can see, I switched. Let's mark this as the line where I switched, and we'll let it go for a little bit, but it's definitely in the 300 range again. for Cuda with using device memory. But again, I'm happier right now with my OpenCL implementation, because if I switch to that, I think I get even better numbers. Yeah, it's like 328 versus 350, 399, but that's close. It's not a big margin, so it's not as clear as 100 milliseconds, but it is definitely looks lower. Even if they're like the same numbers, I still have a preference for writing an OpenCL kernel, because unless I have a real clear advantage to getting my same application done in Cuda, if I gain a great performance advantage, I would rather implement an OpenCL kernel, because that OpenCL kernel, once I've written it, I can use it on Windows, I can use it on Linux, on the host, I can use it on other platforms where with one implementation I can target different platforms. Whereas with Cuda, when I write a Cuda kernel, I'm really limited to just whatever NVIDIA platforms that I use. I can use that Cuda kernel on Windows. I can use that Cuda kernel on Linux desktops. That's great, but there are many platforms that don't have Cuda, and I might be interested in targeting them. So that's what I mean. Cuda kernels are available on many other platforms that are not NVIDIA, but still those platforms have to have an NVIDIA GPU in them. Even if it's a Windows platform or a Linux platform on a desktop, you have to have a NVIDIA GPU in the system. But what if with an OpenCL kernel, I can use the same kernel that I'm using here on the NVIDIA Jetson on the CPU. I can use it on a different GPU on the host, a different brand. In any case, but I do see clearly here that the OpenCL implementation is in the 200 millisecond range, versus the 300s where it was. So I'll mark this line here, and then I'll switch back to Cuda. Mark it again, and right away, well, let's ignore this one because this has to do some sync up of the data between the Cuda GPU and this OpenCL CPU. But there's a good number, but it's still, like I said, it's close. But it will jump. It seems like it's in the 300 range. In any case, I hope that was useful. I wanted to share that and see if at some point I might be able to improve my Cuda kernel. Then I'll share more results, and once I understand the data flows better, maybe there's some tuning I can do to the Cuda kernel to achieve better results. I do achieve better results on the host. For example, let me switch to Windows. Here on Windows, if I run the so I'm running this with Cuda. Let me pick Cuda, and if I run capture, as you can see here, this is the live frame on the right, and as you can see here, it's time exposure. If I move around, it will. If I wave my hands, it should gradually, create a ghosting effect, because it's adding those frames. But what you can see on desktop, it's using a Cuda GPU. It's a GeForce GTX 950. It's a 5.2 capability. It's a Maxwell architecture, 6 multiprocessors. So it's a lot more cores. And now this is still in the early stages, but I'll do the comparison before the overhead for buffer allocation goes away. But it's like in the 9500 range. It's better than what I saw on the NVIDIA, I'm sorry, on the Jetson Nano. Here's the reset button, by the way, so I can reset the time exposure. Here, if I switch to OpenCL, this OpenCL is happening, the same kernel that was running on the Jetson Nano now is running on the same GPU. And here, on my Windows desktop running on x86 64-bit processor with, I believe it has 4 cores with 2 hyperthreads per core. So there's a total of 8 hyperthreads. OpenCL isn't doing as well as Cuda on this. It's the same GPU, same hardware. So all the drivers are from NVIDIA. It's one in the it's in the 200 range and in the high 100 milliseconds, whereas Cuda was in the under 100 or low hundreds. But if I go to ISPC, I get even better results than Cuda, I think. Yeah, 79. So yeah. So I guess, you know, the Microsoft Visual Studio Visual C compiler does a good job. Actually, this is not this is ISPC. This is Intel SPMD program compiler, doing a great job with vectorization and the CPU code with vectorizing using I think it's AVX 256. And then compared to C++, it's definitely ISPC beats C++ here, and it also is better than OpenCL. But Cuda is a close second, or it's a respectable second for my particular implementation, for my particular application. Again, I'm sure I'll learn more about Cuda programming and be able to tune these kernels. But this simple application is what I wanted to use because it's fairly straightforward. Here again, you see at lower numbers. This is happening on Cuda using the GPU. Now, if I go with managed memory, here the cost goes up again, or it's close. So there's really not much difference there. Maybe I'm not waiting long enough, but if I go with pinned memory, it's more expensive. So if I use Cuda, it's better to just use device memory for this particular application. Well, again, I hope that this was useful, and I'll see you in the next video. Take care.